working. High-performance liquid chromatography is incredibly sensitive. It is used routinely for pharmaceutical and industrial analysis, typically of organic substances. For example, using the technique to detect sleeping tablets in blood or other drugs in blood. The relative molecular mass of the substance needs to be more than 300 gram per mole, which is good in that when we were dealing with gas chromatography, the molar mass needed to be less than 300 gram per mole. HPLC can also be used for those substances which happen to be unsuitable for gas chromatography because they decompose on heating. Now the setup is somewhat similar to that of gas chromatography. The pump will pump through the liquid mobile phase. The sample is injected through the use of a syringe. So that is the injection of the sample at that point, and the sample will pass through the column with the assistance of the liquid mobile phase, of course. Now the column contains the solid stationary phase. And the rate at which these substances adsorb and desorb back into the liquid mobile phase will of course differ, therefore expelling the components of the mixture at different retention times to the detector. This is the waste that's passing out at this point. And this just ensures that the liquid mobile phase continues to pass through the instrument. Now some differences here. The size of the particles in the column are 10 to 20 times smaller. The small solid particles will allow for more frequent adsorption and desorption. So more frequent adsorption and desorption. Just move that over. And therefore, with more frequent adsorption and desorption, you're going to end up with better separation, and therefore this particular instrument is more sensitive. The small particle size also means greater resistance to flow, therefore you need that high pressure to pump the solvent through the instrument. And there are a range of solids available, which is quite good, and it allows for increased flexibility within the instrument itself. So in terms of interpretation of the chromatogram, the eluent stream, the stream that passes through the instrument, the liquid mobile phase, the eluent stream is passed through a beam of UV light, and it's worth keeping in mind there that many organic compounds will actually absorb the UV light, so a reduced reading is picked up by that detector, which produces a chromatogram accordingly. As the components pass through the detector, a peak is formed, so just as we found with gas chromatography. Now the position of peaks is the time taken for each of the components to travel from the injection point to the end of the column. So once again, this is the retention time that we refer to. The retention time of an unknown sample, we can compare that to the retention time of a known sample. So unknown sample, comparison to a known sample, and again, it must be under the same conditions if we're going to make comparisons. The area under the peak, as with gas chromatography, refers to the amount of that substance. So this is, of course, quantitative analysis. Okay, so just having a bit of a look at an example here. Here we're looking at the qualitative analysis of caffeinated versus decaffeinated coffee. So regular coffee obviously contains caffeine, and in the chromatogram produced by a sample of caffeinated coffee or regular coffee, we can see a peak at this particular retention time. Now in comparison, the decaffeinated coffee sample, you can see that the amount of caffeine has been significantly reduced, given that the peak that exists at that same retention time is significantly smaller and the area under the peak is reduced. Just note the conditions that have been referred to here, the type of column, also the column size, flow rate, the type of detection that's been used, so it's UV light for this particular sample, and the wavelength has been given there, temperature, mobile phase, and also the sample that was injected. So it's important, if you were going to make comparisons, that these same conditions were set up for running a standard. Whether you're using gas chromatography or high performance liquid chromatography, the instrument must be accurately calibrated using a set of standards. Now the method behind that, a set of standards of known concentration are run through the chromatograph, and a reading is produced for each of those standards. So we produce what's called a calibration graph, like this one that you can see below. So it's peak area versus concentration that we're looking at. So in this instance we have peak height on the y-axis and the concentration on the x-axis. So these have each been plotted. These are the points in which our standards have been produced, and we can use this calibration curve to then read off our sample. So our sample has a certain peak height, and therefore if we plot that peak height based on this value here, we can then read off our concentration from our calibration curve. It's just worth noting that most instruments will in fact do this automatically, but in some situations it does need to be set up. So that sample that you want to analyse is then run through the instrument, and the graph can be used to determine the concentration of the unknown substance. Alright guys, so we've reached the end of the tutorial for chapter 4. I'd like you to do your best to attempt each of these questions here. So as usual, you have your multiple choice questions, a few review questions, and most certainly I would like to see those exam practice questions. Remember, your full work solutions, I'm going to put them up onto Schoology now, and therefore they will be there by the time you guys get this tutorial to run through. Please use those. The only solutions that you won't be provided with are the exam practice questions, so give those your best shot, and you do have the numerical answers in the back of your textbook, so that's always a starting point as well. And we'll chat about this next term. Enjoy the rest of your holidays. See you guys.